the cloud just to be safe, and I can pull it down on the cloud tomorrow. So this evening's speaker is Karen Burnham of EMA, and her topic this evening is software-defined radio EMC applications. Software-defined radios have been around for decades. With computer advances, their prices have dropped dramatically over the past 10 years. SDR hardware can now be purchased easily for under $30, and SDR software packages are available for free for any platform you like. Long beloved ham radio enthusiasts, low-cost SDRs can be a useful troubleshooting tool in the practicing of EMC engineering. In this talk, Karen will demonstrate some of the handy capabilities of low-cost SDR systems, from determining relative signal strengths to characterizing noise or interference signals. Karen is a principal scientist at Electromagnetic Applications in Denver, Colorado. She's an INARTE certified EMC engineer with experience in both aerospace and defense and automotive industries. At NASA JSC, she worked on the Orion spacecraft and pyrotechnic systems. She was able to work on the Dream Chaser spacecraft and the F-35 fighter jet. And I will turn the time over to you now, Karen. And
okay.
Please mute everyone else. Thank you.
Sounds good. So I'll go ahead and share my screen. Okay, so I do that. And then can you should be seeing like a Zoom screen over here. And that. And then I'm going to switch the display settings because it does this every time. Okay, are you seeing a nice looking title slide?
Yep.
Okay, great. So low cost SDR for EMC. Just as Scott said, software SDR, software defined radio, and the low cost part comes from, again, the fact that so much of this has gotten so much cheaper over the last several years. Everything I'm going to show is based on a set that you can get for under $30 on Amazon. It comes with the actual SDR dongle and also 3 antennas and a mag antenna mount. So, I feel like that's a really good deal. So, as a practicing EMC engineer, there's so many handy things to have in your toolkit, right? You need a volt. It's good to have a voltmeter. If you happen to have a vector network analyzer, that's fantastic. Digital multimeter is great. You definitely want some near field probes. If you can get your hands on a handheld spectrum analyzer, that's I love that thing when I was troubleshooting in the lab down at Ford. Current clamps. If you're the kind of consultant like Ken Wyatt, up here in Colorado, he's got an incredible toolkit that he just lugs around with him. Everything from blade antennas, near field probes. I like his broadband EMC or RF noise generator with the piezoelectric barbecue igniter there. But basically, my argument today is that you should consider adding one of these low-cost SDRs to that kind of toolkit, the kind that you can, just use whenever something's going on that you want to investigate. Now, when I'll be talking about SDR largely from that kind of EMC characterizing the electromagnetic environment around us kind of perspective. If I were giving this talk as a ham radio person, obviously this talk would be very different. SDRs have opened tons of new fun things for ham radio people to do, and honestly, there are just about as many applications for these things as you can shake a stick at. So, for today, I'm going to be focusing on the EMC part of it. And I gave a version of this talk back in January. I hope this won't be too redundant for too many people, but I did make sure to add some new stuff. Okay, so one of the things that I wanted to add was a little bit of history, because I thought this was particularly interesting. So, if you look at like the mid 1880s, that's the first time that people were able to show in a lab, basically to measure, create and measure electromagnetic waves. They'd been predicted for a long time. Faraday experimentally had showed that they were probably happening. Maxwell, of course, predicted it. but Heinrich Hertz was the first one to actually generate them and show them. It only took 10 years, 1896, for Marconi to develop his first actual, like broadcast antenna rig. So instead of just a spark gap generator here, you get an actual antenna. That's the one over on the left here. Just pretty much 5 years later, he's demonstrating transatlantic communication. It only takes 15 or so years after that for people to come up with the idea of superheterodyne radio. And that's really the radio architecture that is the vast majority of radios that you'll find today. So when you're driving in your car, you're tuning around your FM radio, you're almost certainly using a superheterodyne architecture. This apparently occurred to so many people that three people filed patents on it at once. And then they spent decades arguing over who was first. But then we really have to skip ahead a bit, because it's not until the 1990s that enough other technologies were invented that software-defined radio became a viable option. And that's kind of just amazing to me to think about, that it took something on the order of 70 years to basically have the next big revolution in radio architecture. And the kickoff for the revolution really was the US military speakeasy program. And I think I love whoever came up with that particular program name. But toward the end of the Cold War, the US military has plenty of money to throw around. But oddly enough, and this was despite going down quite a rabbit hole on Google and Wikipedia and places like that, I could not find any identifiable photographs that are associated with this program at all. But so 1991, the US military commissions this idea. They didn't even call it software-defined radio at the time. That term got coined a couple years later. But they knew that they wanted to have a lot more flexibility in the radio communications with deployed troops. Because if somebody starts jamming the one frequency band that everybody's got a superheterodyne radio tuned to, you really want to have, you don't want to have a whole separate rack of radios. You want one radio that you can, access more of the spectrum with. And in 1994, they successfully demonstrated that concept. Now, in 1994, from what I read, the first software-defined radio filled the back of a truck. And the other thing was that they had spent 3 years coding up this extremely specialized set of software that was tailored for exactly the chipset that they had, or the transistor set that they had. In those 3 years, Moore's law had kicked in. The transistors had shrunk by half, or actually a quarter, because 3 years is 2 cycles of Moore's law. And so the technology had already overcome what they'd spent 3 years coding. And they couldn't just take the code and put it on a new hardware set because they'd made it too specific to the original hardware set. So the program became actually a little bit of a case study for basically for technology overcoming another technology development program. But we go from 1994, when a software-defined radio filled the back of a truck, to to today, just 30 years later. And again, I picked up mine for $30 on Amazon, and that included a bunch of antennas. So now they're just absolutely ubiquitous. There are a lot of different companies out there that make them and sell them, although they're generally all based on the same particular architecture. And there's also a huge amount of software that makes it incredibly easy for people to use. So the one that I'll be using today is Cubic SDR. It's freeware. SDR Sharp is another really common program that people use. I believe Arnie's using SDR Play and doing some really great things, making a low-cost SDR into something, basically a spectrum analyzer. And then if you want to start spending actual money, then you can go up in capability from there. So just to remind everybody, what it is that we're really looking at here. So the superheterodyne architecture, and again, this is the one that's most common, is that you've got your antenna, then picking up all the signals that it can pick up. Then you're filtering that down to the range that you're actually interested in. You're probably going to need to amplify it at some point. You feed that into a mixer, and the local oscillator is going to tune to a frequency such that when you mix it with the incoming signal, it produces an intermediate frequency that's the same no matter what you're tuning to or what you want to pick up. That's what gets amplified, and that's what gets sent to your output device. And it's just a very elegant solution, but it does mean that you are limited to the frequencies that your local oscillator can tune to and still produce the intermediate frequency that the system needs to actually give you output. And so that's really the hardware limitation. So that's the reason why in your vehicle, you're tuning your FM radio, and then you have to switch to tune your AM radio. It's because it's basically two different local oscillators, because one's dealing with 100 megahertz and one's dealing with 1 megahertz. So that's one of the prime limits on the superheterodyne architecture. This is the same architecture, but for FM. And at that point, what you've really added is the phase detector so that you can demodulate the FM signal. But it's the same process of processing the input. And here's basically just a diagram showing that that mixer process. So you've got this relatively broadband signal coming in, or it has quite a bit of frequency content. You mix that with your local oscillator sine wave, you get this beat frequency, and that it retains the modulating signal, either amplitude or frequency modulated, but that beat frequency, by tuning the local oscillator, you can always make that beat frequency the same, so that the rest of the system can actually process it. Now, this is the EMA part. These are the slides that I would consider actually sponsored by EMA, because when you have that super heterodyne architecture, the interference between transmitters and receivers that are located nearby each other, they're predictable to an extent, because you know exactly what's going on in the architecture of each. And so there's a paper that we published with the SAE at the World Congress this year, modeling radio frequency interference between co-located RF systems. That paper was pretty well received, and it's going to be published in the International Journal. And it lays out a system for doing these kind of interference calculations for when you're cramming more and more antennas on the same platform. But no matter how much information you have about those systems. So it's the kind of thing where if all you have is a spec sheet for all the antennas that you're putting on your system, you can do a first cut analysis of what might interfere with what just based on that information. But if you're able to, that's not a good sign. If you're able to get measured data, get more sophisticated measured data, then you'll be able to make that analysis quite a bit more refined. I'm going to pause right there and make sure that my computer gets plugged in, because it should actually be plugged in. Hang on just a second. Had not gotten the plug all the way into the wall. Okay. And then the other thing that's new and special coming from EMA is the automated radio measurement system. So this is basically it's just what it says It's an automated way of characterizing antennas so that you can get exactly this data and be more accurate in your interference predictions. And if people are more interested in that, you can contact Dan, who's on the line right now, or you can go to our website, ema3d.com. Or what would be awesome is if you invited Matt Miller, who's our RF expert, to come talk to this chapter someday, because he's a genius. He knows everything about this world. Okay, sales pitch over. So what is it that makes a software-defined radio special? So as more, as computer processing power got faster and faster, and you were able to pack more and more computing power into smaller and smaller packages, basically, the way to think about it is that you've gone from right to left and started digitizing more and more parts of the superheterodyne architecture. So first you get a digital signal processor, you get digital local oscillators, digital mixers, still with low pass filters, A to D converters to get all those digital samples. And of course, if you're using these as a transmitter, you just run the same chain in advance and it becomes a digital to analog converter. So, just saying SDR is one thing. The older style SDRs might have only used a digital signal processor, whereas the kind of SDR that you might find today has a lot more digital components to it, essentially. So that's one thing to just be aware of as you're looking at different options. And by the way, if you're interested in a lot of the technical details of this, I found this reference, Software Defined Radio for Engineers. It's a fantastic book and it's very well written. And it is actually available for free if you're into ebooks online. So if that's something, if any of this gets you curious about how exactly software defined radio is used and especially how it's used for digital communications, I would strongly recommend checking this out. Okay, so let's talk a little bit about what you can actually do with it. So again, these are screenshots from Cubic SDR, and I'm going to go to a live demo on that in a little bit. But so the first thing is you can just use it as a radio. You can tune to FM, you can tune to AM, you can tune to shortwave radio, pretty much anything that you want to. It has several built-in demodulation capabilities. So FM, narrowband FM, AM, digital sideband, dual sideband, all those different applications. The SDR that I have runs from, I believe it's 2 megahertz to roughly 2 gigahertz. That's its sort of native frequency range, which again is, compared to just a few tens of megahertz for FM radio is phenomenal. And you can also extend that range down to lower frequencies, especially if you're interested in the AM long wave, that part of the, and especially, some of the ham radio applications down there, they actually have a module called Ham It Up, which is basically an up converter that'll take your incoming analog frequencies, boost them up to a higher frequency that the SDR can read and extend down to 100 kilohertz that way. So there's, again, depending on how much money you want to spend on this, there's a whole ton of stuff you can do. So this is showing basically the spectrum that's allocated to walkie-talkies, the family radio system part of the spectrum. And again, I'll demonstrate this live and it's a little bit more impressive, but you can see this is a push to talk, right? So you go from having just pretty random background noise, well, not random when you see those repeated lines all over there, but anyway, you have this ambient background noise. And then as soon as you push to talk, all these turn on and you get your channel that's transmitting most of the data. And then when you stop transmitting, you go back to ambient. So, and again, I want to sort of draw attention to the fact that this kind of plot is giving you a lot of information, not just about, the particular signal perhaps that's intentionally carrying information, but all these other things that have become associated with this signal. So, if I just had another walkie-talkie, I would only hear the one channel that I was tuned to. But having this SDR looking at, a megahertz or 2 worth of bandwidth tells me that I have, an intentional signal here and potentially unintentional signals up and down the spectrum from there. This is a shortwave radio, just a NOAA broadcast from Boulder is the one that I get here. And again, you can see there's the main signal, and then there's a few other things happening in this stretch of spectrum. And, again, there's just so many things that it turns out you can listen to if you have a receive only SDR. There's specific programs that will help you monitor your local police, civic, and emergency medical situations, or spectrum allocations. So that's very much like, I don't know about you guys. My grandmother used to have a police scanner in her small town in Maine, and man, that was her #1 source of entertainment. So, but again, now you can do that with the same soft SDR dongle that you're using for FM, AM, ham radio, everything else. Baby monitors, I had not realized, are are not always encrypted and are using open spectrum. You can listen in to some of the different ham radio conversations going on in your area and your frequency range. When ISS is directly overhead or within your line of sight, you can tune to 145 megahertz and listen to International Space Station communications. Some people are using SDRs for amateur radio astronomy. It is apparently you can tune into the hydrogen lines of certain astronomical objects and monitor them that way for doing some citizen science. 108 to 135 megahertz amplitude modulated tends to be air traffic control. Unfortunately, as Bruce was pointing out earlier, I was trying to see if I could monitor that for the Denver International Airport, which I would think is not actually too far from here, but there are all these foothills and mesas and mountains in the way, and I was not successful at tuning in Denver for air traffic control. But there's also a really cool aircraft tracking mechanism. So apparently aircraft broadcast a lot of meta information about themselves at 1.09 gigahertz. And again, there are specific applications that will, this is the sort of thing you could do yourself, but there's freeware out there that just makes it easier. So it'll take 1090 megahertz data that's called mode S data that's transmitted from an aircraft, feed it into this virtual radar server. And by the way, there's a YouTube link if you're interested in more details on this. And then there's actually a web application that can take all that data that you're pulling from your local monitoring of 1090 and place aircraft on the map, and also tell you if there's anything known about that specific aircraft. So tail number, flag, carrier, what its call sign is, what its route is. So again, I just, before I started researching this, I had no idea that aircraft just broadcast that much information. One more thing, and this is not necessarily what we're going to be doing as amateurs, but SDR has really enabled breakthroughs in what people were calling cognitive radio. And so that's technology that tries to monitor and dynamically adjust itself to the spectrum environment that it finds itself in. So as it's trying to perform some kind of communications task, it will be monitoring its performance metrics, signal clarity, bit error rate, whatever you want to feed in as performance metrics, monitor the overall environment, because again, with the software defined radio, you can get a much broader picture of what's going on around you. And then actually go through a sense, adapt, and learn cycle to determine for itself what part of the spectrum it wants to use at any given moment. So that helps with spectrum sharing. It helps keep everything clear. It can help with multipathing when it finds itself in a multipath situation. And some of these also use smart antennas. So, little arrays of antenna elements that can change their beam pattern, change their beam steering and also change what frequencies they're sensitive to or tuned into. So, again, considering that huge gap from, the end of World War I, we've figured out superheterodyne radio. It's not until, the Iraq War that we figured out how to do SDR. And now we can use it for getting amateur information or troubleshooting information about the electromagnetic environment, but it's also enabling all these much more sophisticated communication applications. So I'm going to switch over to the live demo. I'm hoping that this goes better than it did in January, because in January I had to mute things, and at that point I couldn't hear any questions. But I think I've figured out the better way around that. So if anybody has questions during the demo, please feel free to ask. I think I should be able to hear it. And again, so I'm using a new ELEC SDR dongle. It's any SDR Smart. It's about 2 inches long, really nothing much to it. It goes from 25 megahertz to 1.7 gigahertz. And again, if you get the up converter module, it can go down to 100 kilohertz. It's got, let's see, it's got a mag mount, so I can hook up different antennas to it. This is one of the telescoping antennas that came with the package. And I'm not trying to shill for new ELEC here. I'm really just, trying to show what you can get for 30 bucks. So telescoping antenna, and then it's got a couple that are more tuned to higher frequencies. So let's see. Okay, so when I go there and then I bring up cubic SDR. Okay, can everyone see that?
Yes, we can.
Excellent.
Yes.
Yes.
Okay, so what we're seeing here is just a local FM radio station. And one thing that I really like about this is that you can also see not just the signal where people's voices, either singing or talking, are being broadcast. You can really see the digital sidebands. So a few years ago, everybody switched to having digital sideband information with their FM radios. Well, I mean, I say everyone switched. That was, I'm sure not everyone, but that was the goal. And so one of the things I really like about this is that this is the demodulated signal. So this is actually the people talking. You get this great waterfall coming down. You can adjust where your center frequency is, what bandwidth you're looking at. But another nice thing is you can really tell the difference between a digital signal over here in the sideband and something that's more analog. Again, people talking or singing. And having that kind of visual cue of, am I looking at an analog signal or am I looking at something digital, can be a valuable troubleshooting tool. Again, if you're not necessarily sure what's in the environment around you and you want to just start scanning through the frequencies to see what's there, this is a really quick way of determining some of what's in the RF environment around you. So then if I go to up to 162 megahertz, so now I've got a, this is the local NOAA, so weather report basically coming out of Boulder. When I center on that, but I leave it as an FM modulation, I'm not really getting much. But when I go to narrowband FM, there you can see the voice pattern coming through quite clearly. And again, here you're not seeing as much of the digital content at all. So, again, there are certain things to be aware of. If I was playing around with increasing the bandwidth when you're on a narrowband signal, and you very quickly lose the audio clarity. But depending on what you're interested in, I'm sure again, if you're using this more in a spectrum analyzer kind of way, adjusting the bandwidth can be absolutely critical for narrowing in on what it is that you want to see. And what was the other thing I wanted to say about that? Oh, speaking of the spectrum analyzer sort of application, Again, cubic SDR is a little bit harder to configure into that kind of spectrum analyzer mode of operation. But in that same vein of using this kind of thing to monitor what's around you, there's actually no reason that it has to be an antenna that is plugged into your SDR dongle. It's got a standard SMA connector to it. If you had a current clamp that maybe had an N connector going out, but you had an N to SMA adapter, you could easily use this to take a look at what you're picking up on a current clamp around any particular cable that you're interested in. It's good. It's all RF energy essentially. So there's no reason to consider yourself limited by what you're picking up with an antenna when there are other potential monitoring devices that you could, any kind of RF monitoring device, you could also plug into the same dongle. So let's see, then if I go up to 464 megahertz, and I've got one of my kids' walkie-talkies down here. When we lived in Michigan, we used to enjoy playing hide and seek with walkie-talkies. And so when I do push to talk, you can see what channels are probably most active, but you can also see these others that pop up that weren't there in the ambient. And then the other thing that I really appreciate seeing in this kind of waterfall display is when I push, did you see how everything jumped up, like everything jumped up for a minute? That's a pretty interesting transient that happens when you start a transmission, just that first brief period of time. And if you're interested in exactly that moment of transient, of course, everybody's got a peak hold function. So you can take a look at what that actually looked like and how, again, this is not a calibrated system, right? Yeah, I certainly would not use this to compare against regulatory limits. I wouldn't dream of taking this kind of data and holding it up next to a CISPR-12 limit and seeing if I passed or not. That would be a really bad idea. But in terms of the relative signal strength of what's in the area around you, you can easily see that this is, probably 40 to 50 dB higher than what you've got over here. And that might be particularly useful information for you. Now, the last one I wanted to do.
Can I ask a question?
Yeah.
Is the scale in dB fairly accurate on the software? So it's relative, right? And we talked about the number of dB difference between the two. Is it kind of relatively accurate?
So, like, depends on relatively, right?
Yeah,
Again,
that's the reason to use the word relative. Yes.
Yeah, so you kind of get what you pay for. The more expensive systems, especially ones that do transmit as well as receive, they're let's put it this way, they're a lot prouder of their accuracy than, for instance, this one. So
it might be 10 dB plus or minus 3 dB.
I think that would be fair. Yep.
Okay, thank you.
So now, here's one that I'm actually curious with this particular audience. I'm kind of curious to know if anybody can recognize this one on site. Anybody recognize what exactly caused that particular transient?
Key fob.
Key fob, right. How about this one?
Well, it's a 2 FSK transmission.
Garage door opener?
It could just be a different key fob.
That's exactly it. The first one's a Ford and the second one's a Toyota.
Yeah, one of them was ASK and the other's 2 FSK.
Nice. Yeah, I figured that the folks in this audience would pick up on that just pretty much as soon as I tuned to 315.
Yeah.
But I was very interested to see how differently the waves, the waveform is essentially. When I go to peak hold, it's very strong in that, just in that one peak for the Ford. whereas the Toyota has this, well, just like Arnie was saying, it's just coded differently.
Yeah.
And that actually, that does lead me to something I didn't include in the official slides, but there are folks out there on YouTube. And by the way, I think I'm not too far off base in saying that some people in this audience are probably Raspberry Pi enthusiasts, if I recall correctly. There are folks out there on YouTube who will be happy to show you how you can use a combined SDR dongle like this with with a Raspberry Pi and a particular application and spoof key fobs. So they're very clear on saying only do this with your own key fob. It would be illegal to do that with anyone else's. But
Well,
just so you know that they're
most key fobs from most car companies that know what they're doing are immune to a replay attack of that sort because they use a rolling code.
Oh, nice.
They're encrypted and they use a rolling code. So it requires freshness.
Okay, that is really good to know. But again, that's of the things that people are out there trying to do. That is certainly one of them.
Yeah.
So I went through all that pretty fast, but I'm happy to take questions. I'm happy to, demonstrate anything else anybody wants to see. I know, like I say, Arnie using SDR Play has set up a pretty nice, more like a spectrum analyzer situation. And then I believe that there's a different dongle called a Nano VNA that, again, it's relatively low cost, but it has that same USB interface, but it allows you to use it in the same way that you would use a vector network analyzer. So, there are just so many applications for this technology, and and it's so cheap. It's one of those things where if you don't have the $8,000 handheld spectrum analyzer or the $40,000 huge benchtop level, why not use your laptop and a $30 software defined radio?
Right. I've got a Nano VNA I'm holding up to my camera.
Oh, nice.
That's sure.
So question for the ham people here today. Can this decode slow scan television that the hams use?
I've seen people online at least definitely saying that they could do that.
Okay. What about
you'd have to write a plugin for it, I'm sure.
Yeah.
I don't know that I don't even think SDR Play has a plugin currently for it, but
yeah. Are hams still doing slow scan television? Is that still a thing?
yeah, and they also have a digital slow scan now as well.
Okay. Then what about broadcast like HDMI television? Can it decode that?
I don't know. You'd have to ask the SDR Play people about that. That's pretty high bandwidth stuff.
I see.
Yeah, and quite a bit of processing power required as well.
Okay.
And that's one thing, with cubic SDR at least, well, I can change the bandwidth of what I'm tuned into. So, if I want to see a broader slice of spectrum, demodulated up here, I can do that. But in terms of what you can visualize at once in this waterfall window, that's pretty fixed. You can't get too much of a broader scale than that.
Yeah, see, just you'd be able to like decode those key fob signals, but you'd have to have a plugin written for it. And some of these SDR programs have a plugin architecture so that you can write decoders to use with them.
Okay.
Yeah, Karen, I put something in there. There's a company, Apedis Research, and they are someone who does a lot of serious work around these things. And I bought it out and runs it now. But there's the entire GNU radio, which is software for generically working with the environment of software-defined radio. Has its own conference, well-funded by various government places and military. And then there's also they do a lot of things there. So that's an interesting conference, but if it doesn't exist, someone's probably doing something with it. And they get up to the FPGAs that do a lot more than 2 megahertz, Karen. So
I believe that. Oh, and one other feature that I appreciate is that along with all these other demodulation schemes, you can get the pure I and Q data. The one thing, at least with cubic SDR, I've really had trouble getting it to record that in a file output format that, that for instance, people could compare. So I'm a member of TC3 through the International EMC Society, which is electromagnetic environments. And there's people who are interested in creating something like a crowdsourced database of what you can find in your local electromagnetic environment that you could then upload and other people could look and compare, what's over, what's in Toronto, what's in Detroit, what's in New York. And the easiest way to do that would be to use these exact kind of low cost systems to capture I and Q data, because that's really the most comparable. But if anybody knows like a really good way of getting that kind of file output from one of these programs, I would love to hear about it.
Most of the SDR programs that I know of that allow you to save an IQ output, save it in a .wav file.
That's exactly the problem. Yeah, they're pretending it's audio essentially.
Well, it's but it can be very high bandwidth. That's because the .wav file will let you record stuff of very high bandwidth audio, up to several megahertz.
Right.
But the thing is it's essentially just a raw recording. So at that point, you have to you can play it back into the instrument and then do another decode. If you want to decode, lower sideband or something like that, you can pick out a signal to decode after the fact. Now, if you want to decode something like slow scan television, which only takes up the bandwidth of a audio signal, then what you need is what they call a virtual audio cable. And what that does is it'll take the audio out from your SDR and allow you to input it into another program that normally is looking for input from a microphone input, but instead you essentially have routed the audio from one program into the other. And then you can then run programs that will decode slow scan television or modes like PSK31 or FT8 or any of a number of other modes. Ham radio operators do that all the time. They use their receivers and just plug the audio out from the receivers into the laptop and then run it into any of several different programs to do their digital modes.
Hey, Karen, can you hear me?
Yep. Yeah. Hey, Arnie.
Could you show those two things I sent out?
Yeah, absolutely.
I think I might.
So,
Yeah.
Arnie, do you want to talk to these?
Yeah, this is a Temcell. I call it a Home Depot. And I've been using it for years. And you can make it as big or small as you want. So you put the device under test and the harness in there. And you can see the parallel plate kind of in the middle. So that comes out to a BNC. It tapers down on both ends. One end's 50 ohms, the other end's a BNC, and that goes to my RSP1A. Actually, I put 2 RF amplifiers on it.
Can you hit plus on that a couple of times, make it a little bit bigger? Hit the plus down there and make the picture a little bigger. Yeah, there you go.
Oh, there you go.
Yeah.
So yeah, I've used this for years. The correlation with the chamber is pretty amazing. It's all for relative measurements, but if you fix something here, it works in a fully anechoic chamber. So that goes to a, see, there's a battery below it. You can put that in the cell too, depending on the product and what you're doing.
That's pretty nice. I like that.
It's really useful. You just shut the door, and the dimensions happen to be the dimensions of a heating duct. How about that?
Do you,
Nice.
Arnie, did you make any drawings of that or anything, or did you just
No.
freehand it?
No, I've never made a drawing.
Just freehand it. Okay.
It works great. I mean, it keeps all the external environment out. And below it, you'll see what the result of is of a RSP1A. And it's amazing. I put 2 RF amplifiers because the signal I was looking at was really low. So for less than $10, you can get an RF amplifier on Amazon. So I put 2 of them in series. And this is the before, that's about 1600 megahertz area.
Yep,
And,
1580.
yeah, that's the center frequency, and you can pick how wide it's going to be. They're kind of limited in what you can look at. So you can look at a 1 megahertz spread, 10 megahertz. This is a 100 megahertz spread, and it's really, really cool device. And this is the before. I won't show the after is basically in the noise floor.
Hmm.
And I've been using that for many, many years. Well, actually, I just bought the RSP-1A last year, I think. And before that, I was using an ICOM PCR receiver. This is much better. It's only 120 bucks from Ham Outlet. It's amazing. But the amazing thing, you get an RF amplifier for like $8 on Amazon, depending on how you filter. You go low price to high. You can pay $8 or $27 for the same thing. And it's a hogged out solid piece of aluminum with a cover, and it's got one IC in it, and it works.
Wow.
So
Yeah, there's a
Arnie,
bunch of
what's a-
eBay, bunch of eBay specials like that of various types of, for amplifiers, block amplifiers. Some of them are pretty bad.
Oh,
this one's pretty good. In
Yeah.
fact, if you open it up, you can see what IC they're using, and you look that up. It's a common thing. They use a couple different types depending on which model you get. So it's you can see this one's pretty noisy, and it's I bought this because my ICOM wouldn't go this high in frequency. This goes up to 2 gigahertz. It goes from 1K to 2 gig. It's amazing. So I've used this on all kinds of products lately, and it works.
Yeah.
If you fix it here, it's going to be fine in the chamber. Now you can probably pick apart the TEM cell as far as the dimensions and when it's going to resonate and all that stuff, but it
Oh,
works.
hell, I want one. That's no, that's why I asked. That's awesome.
It works so good. This
And-
particular one, I put the battery outside because this particular product, I can't tell you what it is, but it's every time you boot it up, you get different results. So that's just inherent in the way it works. So it's a lot easier to put a little switch on the outside there. Actually, it goes through RF feed-throughs that you can't see on the side.
Not to hijack Karen's thing here.
Oh, please do.
Okay, so a couple of questions. Why on your septum, I see that you made a 90-degree turn and went down to closer to the base of the duct.
Yeah, there's a 50 ohm termination on the right, although I found it doesn't really matter if it's there or not. Then the other end goes to a BNC that it's got the shell connected to the sheet metal.
Does it go straight out, or do you also go 90-degree bend
No,
down
it
to the
goes
base?
90 degrees. It's just easier because I changed the height of that. Like if I'm putting an instrument cluster in there, it's a little tight. So I have it so you can raise it a little. Again, theoretically, you can punch holes in the theory, but it works.
Arnie, what frequencies are you comfortable using in this one?
This is around 1.6 gigahertz in the middle. And it's about 100 megahertz wide, the problem I was looking at, but I've used it for AM, FM. It keeps FM stations out.
Did you hook it up to the network analyzer to see how you fared with your return?
Yeah, I've got one of those things you showed, Dave. I haven't got around to that. but I do use it for a signal generator. If it's the same one I'm thinking of.
Arnie just became one of my favorite people, gotta say.
This is great. I have to say, considering how much a commercial TEM cell costs, that certainly is a.
Oh, it's ridiculous. It's ridiculous. And
I'm thinking about building one of these. This is awesome. Just a duct, huh? Just an air duct.
Well, and whatever it is they use to block off the ends.
Well, yeah.
It's just a sliding door there.
Yeah.
High
See, it's on
precision.
wood rails. It's nice.
High precision.
Well,
I found at certain frequency, you got to close it all the way or the ambient gets too much.
I mean, didn't we just launch a wooden satellite?
It's the environmentally friendly satellite.
Yeah, it's a wooden satellite. It's made out of plywood.
Funny. That's nice. Well,
if any of you want details, I'll send you more. Again, I've been using this for years.
I test satellites for a living, so I resonate with the whole wooden satellite thing. Just one other thing while I got the floor, Karen. I give talks on passive intermodulation on a semi-regular basis. And your heterodyne receiver diagram is much better than mine. If you wouldn't mind just sharing that, I would appreciate it.
Absolutely.
You don't mind me putting in my pitch, I'd appreciate it. Thank
Absolutely. No, the one thing that bugs me is I got that, I put it together years ago and then I screen capped it so it's not really editable anymore, and oscillator is spelled wrong.
Oh, no way, really?
It bugs me every time I see it.
I'll give you credit for it, and I'll give you credit for that too.
Aw, thanks.
Yeah, no problem.
But yeah, no, I'll definitely send that along.
Okay, all right. Now I'll be quiet now. Thank you very much for this, Arnie. That was fun. And Karen, by the way, thank you for everything you just did as well.
So do we?
Yeah, and Arnie, what exactly is the input to this? When you're getting the data out of the temp cell, what's the input to this this software?
Oh, it's you just go to SDR Play and it's the Spectrum Analyzer software. You just download it for free.
Nice.
It's a little tricky to load up. You got to follow a certain sequence, but eventually you get there. Sure you guys can figure it out. And as I say, you're kind of limited in the bands. It's kind of blurry there, but you just put in a center frequency and how wide you want it to be. So that's kind of a limitation, but it's fine for me. $120. So.
Yeah. I don't know if you saw what I put in the chat, but I put a link to Amazon to an RTL SDR that actually covers from 500 kilohertz to 1.7 gigahertz for $27.95.
Yeah, that comes for, you can pay $8 for the same thing. Just sort by price. Because I got them and I opened them up. And I ordered one earlier for 27. I open it up, it's exactly the same thing. You can get them for less than $10.
Yeah, well, I guess this is the official one, I guess, from the RTLSDR.com folks.
Oh, okay.
It's got the TCXO and the bias T in it.
Well,
Anyway,
you gotta supply a regulated 5 volts to the ones I'm using, which is no big deal. I found that when you power these things up, you can't just use anything. You have to find one of these plug in the wall things with a certain output. Then I put a regulator on it.
yeah.
Some of those are pretty noisy, so you got to experiment. I started out with a battery, but I work on this stuff all day and my battery kept going dead.
You guys ready for the drawing?
Yeah.
Oh, yeah.
Go for it.
Excellent.
Icing on the cake.
So, first question, who is DRO?
That is Dan Odom.
That's me.
Okay. Well, Dan, I'm going to disqualify you. Sorry.
What? What? Gee, what?
It's like
Get 'em
putting
all
it from your
excited.
right pocket to your left pocket,
Rigged,
right?
rigged.
The contest. Sorry about that, Dan. You should have made up another name for me, and then you would have cashed in.
I was going to split it. I was
Those,
going to split it with Karen.
yeah, that'd be our mid-year bonus.
That's right.
So let's get started. Again, the first, you must be present to win. I used a random number generator from courtesy of Google. The first prize will be $100 gift card. The second prize will be $75, and the third prize will be $50 gift card. So the first number drawn is number 44, Yoqing Tang.
Yuching? He was on?
I don't think he was here today. Was he on? I didn't.
Yeah.
Going once, going twice.
I didn't see.
I didn't see you,
Definitely would have said hi.
Okay, so sorry about that. Second one, drawing is number 8, Chris Capel, C-A-P-E-L-L-E. Chris, are you here? If so, turn on your mic.
Don't think so.
Don't think so. Number 3 is person number 22, which is Mr. Malcolm Lunn. Malcolm.
Hey,
Yay.
No.
Yay.
yeah, speak up.
Still there, Matt?
I see him there.
Okay.
Yeah, he's
Muted. He unmuted and said
He's been
something.
on before.
Malcolm,
He
say
said-
something else, man.
He said something and then muted himself.
Matt, we can't hear you.
We know he's here.
Well, I'm here. By the way, Karen, there's lots of things you can do with recording I and Q data. It actually was a ham-sci project just to crowdsource data, as you were saying, to send it in to people. So I sent a link there.
Yeah, thanks. I appreciate that. I will definitely check that out.
You just need a slightly better radio than one of those dongles you've got. Look at a Flex radio, and it's just a bit more money.
Okay.
Yeah, just a bit more.
Okay, fourth one is person number 4, Larry Banaski. Larry? I didn't see Larry's name.
Didn't see him. I would have said hi.
Fifth name is person number 16, Stephen Gladstein.
Yes, I'm here.
Yes, all right. Steve, you
Hooray.
won a $75 gift card.
Awesome.
Congratulations.
Thank you.
Person or drawing number 6 is actually blank. It was I made it go up past the end, so for people who walked in late. So that moves us to number 7, which is person 47, which is Kimball Williams.
Boom.
Kimball, you with us?
I am, and thank you. And while I've got the floor for just a moment, if anybody wants to play with an SDR without going out to buy one right away, in your browser, type in websdr.org.
Oh, yeah.
And you have access to about 100 amateur radio stations around this planet, which monitor all sorts of frequencies, and it's a lot of fun to play with.
It really is.
Okay.
Jim, what was that again?
Websdr.org.
Okay, fantastic.
Yeah.
Okay,
Yeah.
I'm gonna stop the recorder now. I can find the button. There it is. All right, so